coming to the middle part of this week, and that's introduction of orthogonality. So of course we imagine that orthogonal will be something like perpendicular to each other. That's how it is in the plane. We imagine this in the space, but at the abstract level it's very much related to what we call lengths, so definition of lengths of vectors, and what we call scalar products. So we shall actually deal with scalar products, and we shall see that all the rest follows. Right, so just to start with, remember from the plane, so from the very beginning of this semester, that we told that a vector v has got the Euclidean norm, which is computed so that the square is simply the sum of squares of coordinates. So we have to take the square root. From the other course we know we can. So that's good. So we have to be over reals. If we were in the vector space of say vectors over rational numbers, it makes pretty well sense, but we couldn't define it this way because the norm wouldn't exist for most of the vectors. So and at the same time we used the expression where we took two vectors u and v, and we just took the products of the coordinates pairwise and edited the results, and that was called the scalar product. Right, and we told that the angle between the two vectors v and v dash was simply given as a cosine of the angle equal to this expression, right? So the scalar product of the two vectors normed by their norms. So if the vectors themselves, you see that this is actually the upper mapping. So this scalar product is a linear mapping, except it eats two vectors. So it's actually something which we will call bilinear form, right? So it eats the vector v and v dash, right? So and actually I have u and v here, should be v and v dash, right? According to the next formula, and you see that the scalar product is linear in each of the entries, and so if we multiply the entry by the reciprocal value of its norm, then we get a unit size vectors, and for the unit size vectors it will be just the scalar product. So that's the link to the cosine. And now the only thing we have to add is that actually we want to copy this for any dimensions, and for any dimensions it's enough to imagine and to notice that if we want to see something like an angle of two vectors, then we are actually dealing with a concept which lives in the two-dimensional subspace spanned by those two. So who cares about the dimension of the whole space? It must be just the same as in the plane. And that's exactly what we shall see. So in general, we first mimic the definition of the scalar product and the orthogonality as we know it from the plane. So a scalar product is a mapping which is eating two elements from a vector space, produces a scalar. So we shall define it now only for the reals. So orthogonality for us now will be only for reals, right? We shall go further later, but now only for reals. And it should be linear in each of them, and it should be symmetric. It doesn't depend on the order. And we request that if I plug in 2 times the same vector, so on the diagonal of the Cartesian product, it should be non-negative, and at the same time the scalar called the square of norm is 0 if and only if the vector itself is 0. And then what I called already the norm is called simply length or norm. And we say that the vectors are orthogonal, or we can also think of perpendicular, whenever the scalar product is 0, and that's written with this perp sign. And the vector is normalized if its size is 1, its length is 1. And now of course we can ask whether we can always have a basis which is consisting of mutually perpendicular vectors. So all two entries in the basis will be perpendicular to each other and they will be all normalized. If they are just perpendicular to each other, we call the basis orthogonal. If they are normalized on top of that, it's orthonormal. So it's orthogonal, orthonormal. And that's a crucial concept for nearly everything we shall be dealing with in the future. Now notice that if we fix a base, any base, just don't care which base, not necessarily an orthonormal or orthogonal one, then we can evaluate our scalar product on the basis elements and we got some numbers. And the numbers will create a matrix. The matrix will be symmetric because if I swap I and j, it must give the same result. And actually, if I then compute in general how the scalar product works, then I see that it's this. And this is nothing but a general expression of something which we later will be calling quadratic forms, and the quadratic forms are always given by a matrix. This time I call the matrix S. It's consisting of the SCIs from above, and the evaluation is that I multiply with the first argument from the right, so that means that if I fixed y as parameter, then it would be a linear mapping with the matrix S, but multiplied with the parameters in the y transpose. And the y transpose is a line multiplication from left. And this corresponds to the fact that if I fix the x and multiply, then what's remaining is a line. And that corresponds to the fact that if I leave the second slot empty, I must get a linear form. And that's exactly what I did. Right, moreover, if the basis is orthonormal, if it's orthonormal, then we just have noticed that what does it mean orthonormal? It means that all the Sij are exactly as I told before, so they should be mutually perpendicular. So for each I different than j, the value is 0. If I is equal j, then the size is 1, and therefore the square of the size is also 1. So you see that we get a general expression of the scalar product, all the same, which we know already from the two-dimensional subspaces, two-dimensional case. And this is just the scalar product in the sense that you make one of the vectors into a row, that's the y, by the transposition, and you multiply as matrices, and a line times a column produces a number. That's it. Right, now what's nice is that once we know that there is a scalar product chosen on an abstract vector space, so we call it a vector space with scalar product, then we can easily find orthogonal complements to subspaces. That's what we know, right? So if we take a plane in R3, then there will be just the orthogonal line, right? So the orthogonal complement will always have the complementary dimension to the subspace we choose. And how we define it, we simply take the set of all vectors in V which are perpendicular to all vectors in the chosen W, right? So you simply request that your new vectors, these ones, will be, so this is W and this is W perp, right? And here is the definition. And of course, by the very definition, the whole space is always a direct sum of the original subspace and the complement. So in particular, you see that if you take a orthonormal basis, then the orthonormal complement to each one of the basis element, to each of the lines. It's like in the picture in R3 here. So it will be the span of the other elements in the basis. Right, now let's come to the projections. So this is a very nice way of understanding projections. So how would you imagine what is a projection? So if I want to project something somewhere, and I want to do it nowadays, now for us in a linear way, then it should be a linear mapping. And if I project something to a value, then if I repeat the projection, it shouldn't change anymore, right? Otherwise it wouldn't intuitively be a projection. So the intuitive definition of projection is what the people really take, and that's that it's a what's called idempotent. It's just the rule that a square of something is the thing itself. So if I take composition of f with itself, it's f. And then of course I can always write v as the image and the difference between the original v and the image. And the first one is in the image and the other one is in the kernel of f, right? Because here you see if I apply f to this, then I get fv minus ffv, but ffv is fv, so 0. So this also expresses the idea of a projection, and the projection could be that I project the whole R3 in a skew way, right? Not the orthogonal one. But we can define the orthogonal projections as those where the image and kernel are mutually perpendicular subspaces. So each choice of vectors from image and kernel gives us a couple of vectors which are perpendicular. And this is how we understand the orthogonal projection. Right, how to compute projections? The projections are computed in a very easy way, because if you take a orthogonal, if you take a subspace, and if you manage to create an orthonormal base which would have first couple of elements generating W and then the rest generating the perpendicular complement, the orthogonal complement, then of course orthogonal projection means just forgetting the coordinates which correspond to the orthogonal complement, and that's it, right? So that's the content of this. But there is a slight problem with that, right? Because the slight problem is that I was telling if you have or if you manage to get a basis which would be orthonormal and start as a basis of W and then continue as a basis of W complement, orthogonal complement, then we are done. But does an orthonormal base always exist? And here the answer is fortunately very easy, and there is this very famous, very useful and very often met procedure which is called Gram-Schmidt orthogonalization. And it's extremely easy going, because you simply take any set of generators. I will better draw a picture. You take any set of generators, say in the R3, right? So I will have this one and this one and this one. Now I change the color. And what I do is I first just take, say, the first vector, say v1 equals e1, right? And then I make the plane spanned by v2, but I try to find the unique possible combination of v1 and v2 which would be orthogonal to v1, right? So I compute how to combine v1, which is already kept as e1, and v2, which is this one, in order to get e2, is this one, right? And this will be already an orthogonal, and if I normalize, then orthonormal basis of the linear span of the first two vectors, v1 and v2. And now we do the same with the V3. So we simply imagine we have got a parallel plane. So that's what I can obtain if I add something to V3, which is a linear combination of the first two. And definitely I can come to a unique possibility, which would be the E3, which is perpendicular. And that's exactly the Gram-Schmidt orthogonalization procedure. So of course the computer does it without any problem. So you see, we take the first one as the original one, must be nonlinear, and then we seek for the next one as a linear combination of the next one not yet used, plus linear combination of the previous ones. And of course we want to have already the new ones there, right? The V1 up to VL. So here it would be E1, E2, which is used to compute how to get the E3. And then the only request we've got is that the VL plus 1 must be orthogonal to V1 through VL. And this brings you the conditions on the individual AI, because we know that they are already perpendicular to each other, right? So it's rather easy to compute the things, and you get that AI is exactly this formula. So it's straightforward. It might happen that AI will get 0, which would mean that the VL plus 1 was a was in linear dependence of the previous ones, right? So it's not true that every dimension of V big set of vectors will create an orthogonal basis, and then after normalization an orthonormal one, because we need linear independent ones. But it doesn't matter here, because in the procedure you simply lose those losers who are redundant there on the way. So it's absolutely straightforward and in some sense beautiful, I hope. So as a corollary, we see that on every finite dimensional real vector space with scalar product, there always exists an orthonormal basis, and the proof is we take any basis, we make it orthogonal. Now coming back to the projections, if you got W, you know that you can always find a basis of W. You can then find the orthogonal basis of this by the Gram-Schmidt procedure, but in fact you could also just start already with a completion of this basis to the basis of the rest, and then if you compute further via the Gram-Schmidt, you get a orthogonal base of the whole thing. But a good comment on the projections is that, of course, if I go here back, for example, if I would like to project to this space, to this R3, then I have the choice whether I want to find the basis of the line or the basis of the space. And I know that if I project to one of them, then the other projection will be the difference of the original value and the result. So I of course choose to compute the orthonormalized Gram-Schmidt procedure way obtained basis only for the smaller one, because it takes much less time. Imagine instead of the plane you would have 1,000 dimensions there, and then normalizing and finding the orthonormal base for this 1,000 dimensional space would be a nightmare, whereas to do it for the one line is easy. Right, and coming back to the vectors, to the angles, there's already due the simple observation I made in the very beginning. It's just a two-dimensional problem, so you can keep going with the original definition and everything works. And here in the end there is a short couple of notes concerning the multilinear form. So I will not go into details, but please think about it a little bit. So the scalar product is an example of a bilinear form which is symmetric, and what we shall call it positive definite. That was the other condition. But in general, every bilinear form is obtained the same way with a matrix as we saw, and You can also have trilinear, four-linear, and multilinear forms, and we shall be meeting them. We shall be meeting them in the other course as the approximation of our nonlinear functions. So we shall simply need all k-linear forms there. So that's it for this part.